So the thing that's going to complicate this a little bit further is when we don't want to talk about expense in terms of quantity anymore, wherein I want to know directly what price I can sell an item at and know how much it's going to cost me to produce that many items. So this is actually dealing with something in algebra called a composite function. And if you've been through Algebra 2, which hopefully in this class you have, you've seen this f of g of x, right? Instead of substituting a, a number into a function, I'm substituting a function into another function, and that's what's happening here. So if you remember from the last example in the last video, the expense function for selling our phone cases is given by this expense equation right here, which is right now in terms of Q, which is where I get this E of Q from. Well, I've determined that the demand function for these phone cases is given here by Q, negative 66p plus 2250. Well, I want to change my expense function into talking about price instead of expressing it in terms of quantity. This seems a little bit strange on the surface, but we need to do this when we cut into our break-even analysis later on in the unit, and when we start talking about expenses, revenue, and profit later on in the unit as well. Well, so let's look at what I'm given here. Whoops. Actually, maybe I'm going to pick a different color for my Q here, and I'll explain why in a minute. Well, right now I'm dealing with an expense function that's in terms of Q. That's the 17,600 plus 753Q. Well, my goal is to express it in terms of price now. So what I need is some sort of link between Q and P. It would help if I had some sort of rule that maybe expresses Q in terms of P, and lo and behold, I do, right? That's where this demand function comes into play. So in order to turn my expense function into a function of price, I'm going to substitute in my demand function, my Q of P, where I see a Q. Right, we're going to compose these two functions. In order to re-express my function in terms of a new variable. So I'm going to go ahead and simplify this now. Actually, I'm going to use a whole new color just to show that we've done this, right? Expense in terms of price now because my variable is P. So I'm going to distribute if I can find, I'm going to distribute and I get negative 496.98p plus 16,942.50, and I'm going to combine like terms. So my expense function in terms of price now is 34,542.50 minus 496.98p. This does not seem helpful currently, right? This right here does not seem useful yet, but it is when eventually we come to talk about putting this all together later on in the unit. So this is really just a review of composite functions. I'm maybe just writing it in a way or talking about it in a different way, but it's really just composition of functions. Taking one function, in this case Q, and substituting it in for Q in my expense function so that I can talk about expenses in terms of something different. Well, if we want to think about this graphically, we can. And we will, because it's going to set us up for the rest of the unit. So we'll suppose that it costs us $7 each to manufacture one hockey stick. That was awful grammar. The fixed costs are $28,000. And then we also have this demand function given by Q equals negative 500p plus 30,000. And we know that Q is quantity and P is price. So I want to determine and graph the revenue function in terms of price. I also want to, maybe I'll highlight my goals here. I want to know what the maximum revenue is. Eventually I'm going to do this with the expense function as well. I want to know where my intersection points are. So there's a lot of things to do here. Sometimes it's helpful to make a checklist. Let's get to work here. So the first thing I wanted to do is find my revenue function. In terms, I'm just going to abbreviate, in terms of price. Well, I know that revenue is price times quantity. I want to be left with exclusively price. So I need a way to get rid of this Q and replace it with something that expresses Q in terms of P. Well, I have that, right? I have my demand function. So I can go ahead and substitute in the demand function, right? And what this did is it took out Q and re-expressed it in terms of price, right? So these two statements, Q and negative 500p plus 30,000, are equivalent, so I can substitute them. I'm going to distribute to get my revenue in terms of price. I get my negative 500p squared plus 30,000p. So here is my revenue function. Done. Well, the next thing I wanted to do was graph it on my calculator, and I give you, there's a lot of highlighting going on, I give you a calculator window, and that's because in order to figure out this calculator window, you'd actually have to do part B by hand. So in order to save the time, I'll always give it to you. So we're going to use our calculator to find the maximum revenue. So you'll have to excuse the MacGyvered version of my calculator here because my digital license ran out. So while I'm working on a new one, I guess I'll have to deal with this for now. But we want to talk about graphing this function so I can actually work with it. So the first thing I need to do is set my window so I know it appears the right way. So I'm going to press window, and I had said to set your calculator so that x is between 0 and 75. So I'm going to change my x-min to 0, and my x-max to 75. And then I said for y, I said between 0 and 600,000. So I'm just going to do that as well. The next thing I'm going to do is actually enter my function in. So I'm going to go to y equals, and I'm going to type my function in. So I have negative 500x squared plus 30,000x. And here I'm using x instead of p. If I try to use the stored p, you can kind of see it above the 8 on your calculator. That actually stores a number, so it's going to mess up my equation. So we always want to use x, this xt theta n key, to make sure we're doing this correctly. So if I press graph, it should graph. Yeah, just like that, nice and easy. And then we're going to follow a couple specific commands to get to our maximum point. So I'm going to press second and then calc above trace. And then I want the maximum. So I'm going to go down to option number 4. I could also just press number 4. And then it asks me for the left bound. So you can kind of see already on the calculator, right, that right about here is just where the peak is, right? We can just see that. So I want to tell the calculator, all right, zoom in here. And the maximum is somewhere in between there. So I'm going to go up to where this peak is, and then go a little bit to the left. So that way I can see the peak, and I can see that I'm very clearly to the left of the peak. I'm going to do the same thing for the right bound on the right-hand side. I'm not going to guess. I've never guessed. I don't think guessing seems to do anything. I've only seen it mess up the graph. So we're just going to enter right through guess. And you can see that it gives us our maximum and minimum. One thing that we have to be careful with our maximum and minimum is sometimes our calculator doesn't round, as we can see. So just round this appropriately. That's obviously $30. And then you have your maximum. So the next thing we need to know is our expense function. And I was asked to do that in terms of price. So that's going to take a little bit of time. Well, in order to get it in terms of price, I need to start by doing it in terms of quantity. So I'll start with my fixed and variable expenses. So I know my fixed expenses were $28,000 and my variable expenses were $7 per item that I produce, so 7Q. As I said before, we need to find a way to get rid of Q because I don't want Q. I want to express my expense function in terms of price. So in order to do that, I'm going to get rid of Q by making the same substitution I did over here in part A. I'm going to replace Q with the demand function that I wrote for Q. So I have negative 500p plus 30,000. And I'm going to simplify this. So I'm going to distribute, I'm going to combine like terms, and for the sake of time, I'm just going to write out my final answer, which is 3500p plus, negative 3500p plus 238,000. My last step is to graph these at the same time and find the intersection points. And I want to know what is significant about these intersection points. So we're going to return to my MacGyvered calculator setup, which is balancing on a cup so that I can film this. And we already have my revenue function graphed, but I want to graph my revenue function with my expense function. And this is the whole reason that we put expense in terms of price, so that way I can compare things in the same variable. So in order to do this, we need to enter in my expense function. So that's going to be 3,500x, right? Remember x instead of p, plus 238,000. If I press graph, you can see both of my points present. I want to find the intersection points. So I'm going to press second in calc, and I want intersect, so I want number 5. And then I'm asked for first curve and second curve. These are for the same point of intersection. So I'm going to arrow all the way over until I get to this first intersection point that we can see here. So it's going to take a little bit of time. And we're just about there. So I want to be as close to that intersection point as possible, and I'm going to press enter. Now, second curve is only there just to make sure you're as close to that same point as possible, but we want to be on that same point, and we already are, so I'm going to press enter again. Again, we're not going to guess, so enter. And here's my first intersection point. So at a price of about 808, I get expenses and revenue totaling a little more than $200,000. I would repeat this process for the other intersection point, and on my calculator it's being hidden by the first curve and second curve, but I'm going to arrow over just to kind of show you where I'd be heading toward right about there. Yeah, we're pretty close, so enter, don't guess, and there's my other intersection point. So the trick is to make sure you're repeating this process once for each unique set of intersections. So this first curve and second curve, this first curve and second curve. So we've determined our intersections, and the very last thing I wanted to do is just figure out why this is so important. Well, when functions intersect, it means that the functions are equal. So at these points, revenue and expense are equal. Well, hold on a minute, because I had stated before that when revenue and expense are equal, we break even. Right? This is where I have zero profit. So what would happen is that if I pick a price between those values, if I pick something between about $8 and about $59, then my revenue is greater than my expense and I have a profit. Otherwise, I have a loss, right? If I'm less than $8 or if I'm more than $59, I'm losing money. So the importance of these intersection points here is that they are my break-even points. They are my points where I roughly make as much as it costs me to produce my item.